Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our Material Matters mini-series with a discussion of a property that many of you may not have even heard of, Poisson's ratio. Why, you say, should we get to know this somewhat obscure property? The short answer is that it informs us about web and machine quality specifications necessary to meet web and roll width quality specifications. Stay tuned and I will show you the how and why in the next few slides. Width may be the most universally specified of all the web properties. We covered width earlier in great detail in Web20169l. So please review that clip if you have not already done so, because we will be building on those concepts here. Poisson ratio informs us about width and width tolerances. This is true of both the web and the wound roll. Width tolerances, in turn, informs us how good our machine needs to be in terms of tight tension control, tight winder TNT control, and some mechanical concerns such as vibration. So what the heck is Poisson ratio? Quite simple. It is the amount of necking of a material that is under tension. In short, that applies to all of web handling. It is defined as the change of web width divided by the change of web length due to tension. Poisson ratio for most simple materials is close to 0.3. However, for structures, you can get very different values. For example, with some nonwovens, the ratio can be 3 or 10 times that of typical materials. That means, in short, that the width changes are greater than the length changes when you apply tension. Poisson ratio inside of wound rolls can get even stranger. So, how do we measure Poisson ratio? If we are lucky, because this is a difficult test to do, we could merely look it up on the internet. If the internet does not have a value for Poisson ratio for our product, we have to invent or contrive some tensile test fixture to measure it. It is done with something like a tensile test. We pull a web with a good fraction of yield simply to get better measurements, then somehow measure the changes in length and width. For low modulus nonwovens whose properties are not on the internet, I try to hang a very long specimen against a wall and deadweight it. Length and width before and after applying the load is recorded. Of course, that simple method would not work for stiff materials because the strains would be too tiny to measure with a ruler or tape measure. So, how do we apply our newfound knowledge of this once mysterious material property? The first is how we would specify slitter blade to slitter blade distance and tolerances, as well as tension settings to get specified product width. The second is to set the maximum tension variations and Poisson ratio variations that keep us within product width tolerances that our customer is expecting. Meeting width tolerances can be quite challenging whenever any of the following is true. The modulus is low, or Poisson ratios are high, or width tolerances are tight. From our must-have 750-page Web Handling Handbook, we can illustrate the challenges with a couple of ordinary examples. For a low modulus web, tension will neck the web by only 0.3%. For a low modulus non-woven web, tension will neck the web by an incredible 3%. This is an in-your-face width variation under almost any situation. Not only might our customer be concerned about web width, they may also be concerned with roll width for any number of reasons. As we briefly introduce this topic in Web20169l on this all-web handling channel of YouTube. In short, roll width is guaranteed by the laws of physics to be non-uniform. Review that clip, or better yet, take my advanced winding section of my award-winning and trademarked Web 101 to get all of the details. As we learned in our Web 101 class, physics only allows 3 solutions to truly flat roll ends, and none are commercially viable. The first is to wind under zero tightness. The second two involve cutting widths, but they only change one width problem type for another width problem type. Again, see our Web 101 class for details. While we are on the subject of roll edge quality, we might briefly mention that tension variation or machine vibration will make rough roll edges. The result is also guaranteed by the laws of physics. The best defense is a strong offense, as the saying goes. The best defense here is to literally go to school and learn what is allowed by the laws of physics before you commit to product or customer specifications. There are 2 places where you will learn more about tension necking and its application. The first is the must-have 750-page Web Handling Handbook written by myself, Tim Walker, and Dylan Jones. The second is my award-winning and trademarked Web 101 class that has been taken by 5,000 students just like you. Here you will learn how to use material properties and testing to size and maintain and operate and troubleshoot web machinery. Thank you so very much for joining me in this Material Matters series. Stay tuned for the next clip where we will discuss porosity and permeability, what they are, how you test for them, and why it is super important for some web products. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. Also, please consider supporting the work of this channel using the Patreon link below. See you next time.